replacement method. The process is not difficult, right? 3 steps. In the actual calculation, once you get the S, I don't think you are going to have a good number. You may have complex number. Because usually your pole, your zero are in complex domain, right? So once you have a complex number, you put your complex number S here, E power ST. So there can be 2 scenarios because some student told me his calculator cannot calculate complex number. So 2 scenarios. One scenario, if your calculator can calculate complex number with the exponential function, then your task is very simple, right? So for example, your S is 1 plus J. Then what it is? Then you just use your calculator to calculate E power of 1 plus J, right? Then you get a complex value, then which is your Z. But if your calculator don't have, okay, the capability, and don't come to ask me how to use that. I haven't used calculator for many years, and definitely I don't know how to use your calculator. That one beyond the capability. I only know how to use MATLAB. Unfortunately, so later don't come to ask me how to use your calculator. How to use your calculator? Look at your manual. But in case your calculator cannot calculate complex number, there is still a way to do. Then you need to follow this. Then your ST, after you multiply with ST, you get your E power minus AT plus your JT. Plus your BJT. Then you need to do 2 parts. Your real number will come out the magnitude R. The imaginary part will come with a phase angle E power J theta. Then this one will become your cosine, sine, and so forth. Just in case your calculator cannot calculate your E power J theta at all. Okay, I hope you know what I mean. Okay, this is something extra and nothing to do with cost, but it's just for some of you to calculate. So for E power A plus JB, for example, you have both real part and analog part, right? So this one can be your E power A and E power JB, right? So this one is your R. And this one will be your cosine sine part, right? So this is the other way, but anyway, I think the simplest way is just get a calculator. If possible. I think I give another thing which I possible. Okay, understanding is you just learn your state space, your continuous domain, right? And the only difference is in your continuous domain you're using ABCD. Okay, because this one we follow the textbook. The textbook uses FG and J. ABCD is just a different single equations. Okay? Because classical science we adopt 2 different textbooks, and one textbook uses ABCD and FGHJ, then anyway, follow FGHJ. So we want to focus on how to cover, okay, because this one will just cover your continuous domain, so this is one. So I think in your continuous domain you cover exactly the same example, right? Your mass and in system. So So you're able to convert from your transfer function to your state space function. You're able to get your transfer function from your state space function as well, right? So basically, you're able to do this conversion. These are some of the formula for you to convert between your state space and your transfer function. And there are also certain method code if you want to use. And let's do some of the exercise, okay, just to review or do some warm-up on the visualizations. So let's see a simple transfer function 1 over x squared. Can you determine the state space function? You how to determine? How do we get this one? So first of all, you get the transfer function, which is 1 over s squared, right? And the transfer function basically means your output divided by your input, your y, s divided by your us is equal to 1 over s squared. Then we represent into a differential equation. Your s squared means your s operator is a differentiation, right? So s squared basically is second order differentiation. So you differentiate 2 times, right? So we do the inverse Laplace transform, we convert the S domain to the time domain. Basically, the first thing you need to do to convert from your transfer function to your state space. The transfer function is what? Is in your S domain. It's after Laplace transform. By your state space, the state space is in the time domain. So basically, you need to convert the time domain first. You need to get back to your differential equation first. So this one I get the second order differential equation. So how to design a state space function? That one I believe Dr. Idris has given you a lot of good techniques, right? So you got many ways to design a good state space function. And please pay attention. For the same differential equation, it's not one-to-one matching of the state space function, right? It depends how you define your state vectors. It can map into different type of design. Okay, so the solution I'm showing you is just one n. Okay, not necessarily is the only one. Huh? So we do a simple thing. Because you see this is just a second order differentiation. So I just come out a state vectors and each one is just a differentiation of the previous one. So I define x1 as a differentiation. Sorry, I define x2 as a differentiation of x1. Then my differential of x2 is my input. Because why I design so? Because this is a second order. So I need to differentiate 2 times. So if definitely ut should be my input. So one state vector, one element of the state vector should be one time of differentiation at least, right? The second one, I will differentiate again. So I have 2. So my y will be my output is 2 times differentiation. So y is just your x1. So if I define so, then my state space is pretty simple. My differentiation of my state vectors is just a very simple matrix 0, 1, 0, 0. Okay, how we do the matching? How do you do the matching? Because x1 differentiation is x2. So it's just 0, 1, x2, right? x2 differentiation is u. So this one I have nothing to do x1, x2, only have u. So this is how I get my state space. Then for my y is very simple because only refer to x1. So just 1, 2. Of course, if you want, you can design another state space to get equivalent differentiation, equivalent my FGH, right? So this is how we get the FGH in the state function, the state space function. This one, I believe you have covered this one. We started doing this already. Now, in my class, we are going to focus on how to get the equivalent digital discrete functions. So, in the space function, if we are going to see a digital one basically is represent your differentiation into a time domain, right? By difference function. A different function basically is a function with a time domain. So we want to see what the difference between your continuous state space and your digital state space. So in your continuous domain, it's a state vector. Okay, I purposely put the error there, represent a vector. So we have a state vector. Then do the differentiation. We find the first order differentiation of a vector. We get the state space function. Then my output is just certain scaling of the state space vector, right? So just H times vector A multiplied with vector. Then how about the digital one? Digital one, instead of differentiation, we see a difference equation. So instead of X store, I have K plus 1. So with a continuous time domain, for differentiation, we do a difference equation. So horizontally, we also have matrices for the xk, matrices for the input uk, and my yk output just fk. So later you will see the main difference is how to convert a differential equation into a difference equation. And later I will show you two approaches to do so. One approach we can do to get a discrete state space function is we can do the conversion from the FGH. Because basically, for you to define a space function, you need to have your FGH. You need to have all those coefficient matrices, right? So these are the formulas. Okay, how they are going to divide. Okay, for those students who are interested, you can refer to the textbook. So this one will show you how to define. And it looks complicated. And in practical, usually you will see this one after certain terms, you see a lot of zeros. So once you have zeros, then for the future ones, that's it. It's supposed to be infinite Taylor series. Are you familiar with this one? I think you should learn this one in your when you learn your definition of integral function, right? When you learn the definition of an integral function. This one is equal to a Taylor series, right? And this one is basically your Taylor series in a matrix form. Because this one can be your 1 plus your x divided by 2 plus your x squared divided by 3. Sorry, so x divided by x squared plus x n divided by n. This is something I think you have done before, right? The Taylor series. How to define your p-value, right? Yes or no? Okay, anyway, this is something I learned. And this is something important for us to do the explanation function in matrices. So this is the key function. If you have a explanation function in matrices, you can extend it by the Taylor series. This is a I matrices, I matrix, or the identical matrix. Okay, then your F P, your F square, P square, divided by. And I understand this one is looks a little bit confusing, so now I show you a particular example. But before that, let's get the full picture first, the big picture. This is your transfer function, GS. So I believe in your analog control part, you have learned how to convert the GS to your state space. You can also convert your state space to the GS. So now we have a two-way to get equivalent discrete equivalent functions. One way is from the transfer function, you get your continuous state space function. Then you based on this formula, you convert to get your 3 or 4 coefficient matrices from your continuous domain to the digit domain. This is one. Get your continuous transfer function, then get your continuous state space function, then convert to your integral state. We also got the other approach. Because this one is find out the equilibrium based on the zero of the pole and sample equivalence. So you can use the sample equivalence of the zero of the pole from what we have done last time. Use GS divided by S to the Z transform multiplied with 1 minus Z. So you will get your Z transfer function. Then you can convert this one to a digital or discrete state space. Because on this one you can get a difference equation. After you get the difference equation, you can rewrite or regenerate your difference equation in the state space function. Okay, we are going to show both approach by the same transfer function. So we look at this transfer function 1 over S squared. Our first approach, we have get this one into a state space function. This is the state space function. Right? This is my F, this is my G, this is my H. So now I'm going to digitize your F, G, H. So how to digitize it? I want to get the phi, tau, and H. H actually no change. So basically a median group of these two. So how to get the phi? Based on the formula, phi is basically the input of Ft. So we use the Taylor series to explain it. We got identical matrices plus Ft plus F square, D square divided by 2 and so on. And here, your F is a matrix. Okay, T is a constant. So what we are going to do? Identical matrices is very simple. It's identical, so the vector is 1, the rest is 0, right? So we have 1, 0, 0. Then what is F? Your F is 0, 1, 0, 0, right? So your Ft is 0, 1, 0, 0, T, right? Then how about the F square? F square is F multiplied with F. So you 0, 1, 0, 0 multiply with so what you get? 0, 0, 1, 1. So what you get? Basically, as long as you see a vector which all with 0 elements, you will see forever multiplication you will get 0, right? So what you get? But now you get something you want. Because I prefer 0. Once I get 0, I can guarantee your f power of 3 also. Your f power of no matter what it is, greater than 2 will be 0, 0. Right? It's a 0 matrix. So anyway, the rest are zeros. So what you have? You only have 2. One is the identical matrix, one is your FT. You alright? So what you get? You get your first coefficient matrix, which is 1, T, 0, 1. Right? And this is the same thing. You see the E of F, at the end you get 1 T 0 1. So if I change the T to gamma, what do you get? 1 gamma 0 1. Anyway, this one is just a constant value, right? So if I just substitute because it's the same thing, if you want, you can make it the same calculation, but if you get this one, right? So it's not one. Now my second, if you want to. So I complete the 5 already. Now my second one, I need to calculate the power. The second coefficient. So this one is the integration of E power F gamma. Okay? So this is the reason I need to get equal to this one, right? This one. And this one is this one. After I get this one, my integration will become this one, the integration is much easier, right? Because this one is 1, so that's why you put the integration what you get. You will get T. Then this one is like the first order, what you get? Half T squared. Then multiply with G, then I get half. But how? When you look at the formula, it's very complicated, right? But that might really depend. If you have a simple order, for example, the example we have now is a very simple one. So you have a lot of 0 and after you multiply 2 times, you get 0 and but if you got a very complicated system, your calculation will be very crazy. Then you will need to use your computer to calculate. So after that, you are able to get your second coefficient, right? Then what is the third coefficient? The x still the same as your x. So your f remains the same. So this is the way you can get your discrete state-space function.
It's
you get your space digital space function. If you want, you can also get your transfer function gz. Right? The conversion between your space and your transfer function. So this one I got my x already. I got my 5 already. Already. So if you want, just a mathematical practice. This is your S. And this is your identical. And this is your 5. And this is your half. And this is your matrix inverse. So after you do all this, then you get something. Is it something you have seen before? If you have done one of the two, the so-called exercise. 6, right? Ask you to find out the zero order co-equivalence of 1 over S, right? And at that time you get this one, right? So basically, you can find your GS divided by S, do the Z transform, multiply with 1 minus Z power minus 1. You get this one, right? This is something you have done through your exercise question, exercise 6 or 7. Now, what you can do, you can also do this, convert to the space, digitize the space, then convert to the function. Okay. Now I have shown you one cycle, right? Any questions before we move on? Now we have shown you one cycle, but GS, you get your space, digitize your space, you get your GZ. So you finish one cycle, right? Now, why don't we do another one? GS, digitize, get your GZ, then you also get your digital discrete function. This from your GS to your GZ also can be considered one of the solution to the exercise question, right? So basically this is from your GS. We apply the sample until order to get your GZ, right? So this one is not difficult, right? 1 over S squared divided by S, you get 1 over S squared. Then this one you look the Z transform table, you get this one. You multiply with 1 minus Z power minus 1. Then you just simplify it, you get this one. This one should be the same as the one we calculated before, right? You can see we have the same thing. So now we get this Z function. This is GZ. So from GZ we want to get a digital space function. So what should we do? This is the Z function. So similar approach as how you convert your transfer function, your continuous domain to your space. You need to come back this one to a difference equation. How to rewrite your Z function into a difference equation? Basically, your Z operator is just considered as a delay, right? So my yz divided by uz equal to d squared divided by 2 multiplied with z plus 1 divided by z minus 1. So I expand it. My y z multiplied with this one, z square minus 2z plus 1. Can you see it? This one, together with this one. So I get this one. Then the remaining part, get this one. Alright. You have a z square, it means you have a 2 time delay. You have z means you have 1 time delay. You have a constant, it means just your yk. Here the same thing, you have a z, it means the 1 time delay. You have uj just go to the yk, or go to the uk. So this is basically how we obtain the difference equation. So this is a difference equation. So of course, when the difference equation convert to your state space equation, you will also have many multiple choices. Okay. So one of the thinking is I observe. Because usually I prefer to see the difference. So if I rewrite this one into yk plus 2 minus 1 yk plus 1. There still remain as a minus 1 yk plus 1, right? So I minus yk plus 1. Then my plus yk becomes minus yk. So now I can see this one become two-step difference. Right? My difference between k plus 2 and k plus 1, and difference between k plus 1 and k. And here you can see your remaining part is also half t squared uk plus 1 and half t squared uk. So now it needs me to think, because I want to think about the difference equation. And difference equation, if I represent this one as a difference divided by t, so it's something like a differentiation, right? It's something like differentiation, approximation of differentiation. It's a difference divided by t, right? So if I get this one, I get this moment. Then from here, I can design some of the spaces. So if I define x1k equal to yk, then my x2k can be your x1k plus 1 minus x1k divided by t minus half t uk. So basically, I'm consider this part minus this part. Because this is actually your k plus 1, k plus 2 mapped into your k plus 1 increase one more time. Then the remaining part, you can also have a two-dimensional data. So this is certain techniques. After I define the state vectors, then my state space can come easily. My x1 k plus 1. Because remember, for the state space function, what you are looking for? For state space function, you are looking for x k plus 1 equal to so we are looking for a format which represent your k plus 1 by a vector of k and uk, right? X k and uk. So here I want to find out what is x1 k plus 1. So your x1 k plus 1, the x1 basically is your y. So it's your y k plus 1, right? So this one is equal to your x1k plus t x2k plus half t squared uk. Where did it come from? one here, your x1 k plus 1 equal to x1 k. Then your t multiplied with x2 k, then plus your up t squared. Because you get multiplied with t, right? So your up t becomes up t squared. So I get x1 as a function. x1k plus 1 the function of x1k and x2k. Then for my x2k plus 1. So this one x2k plus 1, this one is the one. So this is the thing in blue. So this one in the blue box. This is basically your x2k plus 1. Then I see this one is equal to my s1k plus 2 minus so eventually I equal to this one here. But here, this one you can consider as your x2k plus 1 and this one is x2k. Then you have your k. After I obtain a function x1k plus 1 as a function of x1k and x2k, x2k plus 1 as a function of x1k, x2k, uk, and so forth. Then basically I get those are simultaneous equations already. Then my next step only have to rewrite your simultaneous equation into a matrix form. So how can we write? Let's see a clear form. So this is what we look at. So x1 k plus 1 is a function of x1, x2, and uk. x2 k plus 1 is a function of x1, x2, and uk. So we rewrite in a metric form what you get. x1 k plus 1 equal to 1 times x1k, t times x2k plus half t squared multiplied by uk. So basically this is my first equation. My second equation, x2k plus 1 equal to x2k. So x1 is 0, x2k is 1, uk t. So this is how I get my state space function. So now, if we refer back, this is if we refer back to what we have derived previously, they are identical and the same. Okay? If you see what is the previous one, they're the same. But here, what is our edge? My yk is equal to x1k, right? This is based on what we have defined here. So basically, your matrix is just 1, 0. So this is your matrix. So now, in the interest, you see, you get the same TS. We digitize it, you get the equivalence root of 0 to 4 plus the sample equation, you get the GZ, right? So from the GZ, we extend it out, we get the difference equation, then we rewrite the difference equation to the state space. So basically, it asks me how to get a digital state space function from a continuous GS. If you are stuck on here, there are two options. One is you get a continuous state space, then digitize it. Then this one you get a good integration, And for the integration of the exponential function, you may want to consider the Taylor series. Okay, and you the exponential function matrices. Then you get your digital space function. The other approach, you can get the zero order whole equivalent digital function CZS. Then you cover this one with your difference equation. Then from the difference equation, you can get back your digital state space. But of course, if you already have your state space function, you want to digitize it, then you just do this one. You're not supposed to do this, and this. If you already got your digital transfer function already, you want to find your discrete function, then basically you will go back to the difference equation, then from the difference equation you get your space. It's similar step as your continuous domain. You get a difference equation, you get a differential equation, then you represent a different equation. But here you get a differential equation, and by the differential equation you represent your state space. So basically your state space is a form to represent your differentiation, to represent your difference equations. The good thing for your state space form is they always to be only first order. They always to be first order differential equation. But where the order comes from, where the order goes. If your GS, in my example, the GS just now is the second order. If it's second order, convert to state space. Your state space is the first order. Then where is the remaining one S goes? Basically, your second order becomes a 1/2 vector. Right? Your order of differentiation convert to the order of the vectors. Convert to the order of the matrices. If you are interested for an order of differential equation, convert to the state space. Your state space always will be first order differentiation, right? Then your order of your matrix will be n by n. Then your state space vector will be nth order. So basically, they convert your high order differentiation to a high order of the matrices. Okay? And similarly for the digital one, your difference equation, you have a many delay. If you are n order, you have an n delay. Then your n delay will convert to nth order of your matrices, or nth order of the vectors. So here you will also see your vectors are 2 by 2. So your vectors are 2, and 2 by 1, and your matrices are 2 by 2. If your transfer function is 3 times, 4 times, n times, then you will see your vectors will be nth order, your matrices. Okay? So these are some techniques. If you are interested to apply your state space forms in your controller design, in your system analysis, and later eventually you are going to implement, you need to consider the digital form. Okay? So this is the conversion from the analog form to the digital form. You may also want to know how to convert from a digital equation, a digital transform function, to a difference equation, then to the state space form. After this, we will conclude everything under the next slide on the technical and classical and empirical. And this one particular is covered as even though the depth as a matrix, but actually at the classical side and the date, it also cover classical structure. Okay, because you put like analog parts, okay, finish. So that's all for today. And also as I mentioned, for those who are late, this Friday you have a revision class in the morning, okay, by Dr. Matthew class. Okay? And next week, Monday, I will still be here. questions, you have anything regarding this particular you want to discuss with me, you're welcome to come. Okay, I hope you know